turn over along the way. All right, Chemistry 3101, we are moving into chapter 15, which is right here. And it's the chapter on nuclear magnetic resonance spectroscopy. And if you're wondering what the thing is here, is this like our 2D2 or something? No, that's an NMR spectrometer. And at UCCS, we have two NMR spectrometers. But before I even get into the introduction of NMR in chapter 15, I want to explain to you why NMR is so important. So when we talk about nuclear magnetic resonance spectroscopy, I'm going to just refer to it as NMR spectroscopy. So when I say NMR, that's what I'm talking about. All right, so if we were to compare a couple of compounds, let's say we had two compounds that have the molecular formula C4H10O. Okay, so I'm going to draw a couple of compounds here. So this is called diethyl ether. You guys can obviously see that that's an ether. And if I compare that to butanol, so this is called 1-butanol. If I compare those two compounds, and if I was to run an IR on those two compounds, could I differentiate between them very quickly? The answer is yes, because you would see the big old OH stretch, right? For the alcohol, you don't see it for the ether. And so you'd be able to tell these two compounds apart very, very quickly using IR. You wouldn't, MS, it might be a little bit more difficult, but you know that in the mass spectrum, the alcohols, they will lose 18. So you might see M minus 18 in the spectrum. But anyhow, and then again, I'll put here the OH stretch in the IR. So could you differentiate between these two compounds using infrared spectroscopy and mass spectrometry? The answer is yeah, absolutely you could. Well, let's take that molecular formula a little bit further. What if I wanted to compare these compounds? Let's say I had that same old butanol, so 1, 2, 3, 4. Let's say I had this isomer of it, which is also an alcohol. This is called 2-butanol. And let's say I had this isomer. Okay, this is called tert-butanol. Now it gets a lot more difficult to differentiate between these three compounds using IR and mass spec. Why? Because in the IR, these all have an oxygen-hydrogen stretch in the IR. Okay, so IR would be tough. Okay, and then the mass spec, well, they're all going to have the same mass spec, the same molecular ion. They're all going to lose 18, so it would be tricky. And if you're thinking, well, what about the fingerprint region? Could I use that? Sure, but you kind of have to dig around in the fingerprint region to figure out, which one is which. However, after you have covered this chapter, chapter 15, what we're going to talk about is what we call proton, so hydrogen 1, proton NMR, nuclear magnetic resonance spectroscopy. And if you were to run a proton NMR, so a proton nuclear magnetic resonance spectrum on these three compounds, you could tell them apart in probably less than 10 seconds. Okay, so NMR is a very, very, very powerful technique. And if you're wondering, do you mean I would be able to? I mean, any of us. Okay, I'm talking about my students. At the end of this chapter, you would be able to tell the difference between these three in about 10 seconds. Okay, you'd be able to say the first one is the primary alcohol, this is a secondary alcohol, and this is a tertiary alcohol very, very quickly. And why is that? It's because NMR gives us information about the way carbons and hydrogens are attached to each other. Well, what are the two most prevalent atoms in organic compounds? It's carbon and hydrogen. So if we can get information about how they're connected together, and we get those little puzzle pieces, we can put them together and come up with a structure of the compound. Now, if you're saying, well, okay, if this is so great, does that mean I'm just going to throw my IR and my MS in the garbage? No, not at all, okay? Because normally when we characterize or when we prove the identity of an organic compound, we use a combination of NMR, infrared spectroscopy, and mass spectrometry. So we would use all of them together, all right? Give me a thumbs up if you're if you're with me on the reason why we study NMR. Okay, it's not about functional groups this time. It's not about mass. It's about the way the actual molecules are connected together. And you see that these three molecules are obviously connected together in a different way, right? They're all isomers of each other. Okay, before I get to the next slide, let me share one more thing with you. Okay, so you guys probably remember this formula. We saw it in chapter 14 that energy is equal to Planck's constant times nu. Okay, so we know that energy is directly proportional to frequency. So if we have a high frequency, we have high energy. Okay, Well, something else that we're going to see is that in the nuclear with an in nuclear magnetic resonance spectroscopy, what we use is a big magnet. So if you're wondering what this is a spectrometer, and inside the spectrometer there's a very powerful magnet. I'm talking about so powerful that if you have a pacemaker and you go near this magnet, it will kill you. Okay, so it's a very powerful magnet. Now, Mr. Dion doesn't have a pacemaker, but Mr. Dion carries a wallet. And my wallet, inside I have my credit cards and my debit cards, which have magnetic strips on them. Do you think Mr. Dion has ever put his wallet next to the spectrometer and erased them all? Oh yeah, oh yeah. I'm ashamed to admit it, but I've done it. Okay, by accident. So, anyhow, in here we have a big magnet. Okay, so let me use a finer tip here. So inside the spectrometer we have a big old magnet. Okay, a very powerful magnet. And the way that we represent a magnetic field is we use B0. Okay, like that. Okay, so we use B0. Now, the reason I'm telling you that is because we're going to talk about energy a lot in this chapter. We're going to talk about frequency a lot in this chapter. And I want you to know that energy and frequency are directly proportional. Yes, they are, but they're also directly proportional to that big magnetic field. Okay, so energy, frequency, and the magnetic field, they're all directly proportional to each other. Okay, this is a very, kind of simplified way of looking at it. Some of the math can get rather complicated, but the bottom line is that energy is directly related to frequency. We already know that. So high energy is high frequency, and high frequency is going to be a high magnetic field strength. All right, there you go. So that's kind of my introduction to the introduction. Okay, the NMR spectroscopy. Look what it says here. Okay, these are David Klein's words. These are not Mr. Dion's words that Mr. Dion is pontificating or something. No, this is the author of the textbook says it may be the most powerful method, okay, for gaining structural information about an organic compound. Okay, now why do you need to know structural information? Again, what's one of the major points of studying organic chemistry? Well, one of the major reasons that a person would want to be an expert in organic chemistry would be to develop new medicines. Okay, so let's say you develop a brand new drug. Okay, so we'll just call this, here's our compound. It's just a circle. It's like the simplest, or the silliest molecular geometry. But let's say you make a new compound. It's an organic compound. And let's say we'll put drug ? Okay, we think this drug might be able to cure cancer or some kind of orphan disease or something. Well, you can't just say, okay, I put this drug inside a person and it has the desired therapeutic effect. Therefore, I'm going to put it on the market. The FDA is not going to let you do that. Okay, they want to know what the structure of the compound is. Okay, well, you can't shrink yourself down to the size of an atom and with a camera with your phone and start taking pictures. Okay, you have to prove the structure of the drug using spectroscopy. So what are you going to use? You're going to use infrared spectroscopy. You're going to use mass spectrometry, but you're also going to use NMR, nuclear magnetic resonance spectroscopy. And these three all together in conjunction are going to prove the structure of that drug so that an educated scientist is going to look at those spectra and say, well, I can't argue with it. This is the structure of the compound. There's no debate about that. Okay, and so we covered these two forms of spectroscopy and spectrometry in chapter 14, and now we're getting into NMR, which is this chapter, chapter 15. And if you're wondering, hey, Mr. Dion, are there any other types of spectrometry that we would use? Yeah, sometimes we use things like LCMS, which is liquid chromatography mass spectrometry, and there's probably others as well. Sometimes you might even use something called X-ray crystallography, which is a way to prove the absolute configuration of a molecule, but that's neither here nor there. Okay, what we're talking about right now is NMR. So very powerful technique. And NMR, just like infrared spectroscopy, involves the interaction between electromagnetic radiation and the nucleus of an atom. Okay, well, let's unpack this for a second. Electromagnetic radiation, which is light. Okay, when we talked about infrared spectroscopy back in chapter 14, right, in infrared spectroscopy, we talked about infrared light. Okay, but now we're talking about NMR, so NMR. We're talking about the radio frequency of light, so radio waves. Okay, so radio waves, and so oftentimes we just say the RF frequency. Okay, but and if you're like, well, aren't those like really big waves? Yes, absolutely. Okay, so the waves aren't dangerous to us at all, right? There's radio waves going through all of us right now. Okay, because telecommunications use radio waves. So if you're like, well, what's the dangerous part again? The dangerous part is the magnet, okay? The magnetic field. That can be dangerous if you get close to the magnet. So what are the nuclei that we're going to be looking at when we talk about nuclear, right? Nuclear magnetic resonance. Well, the two nuclei that we are interested in as Chemistry 3101 students are going to be carbon and hydrogen. Now, why would that be? It even says here, for obvious reasons, right? What are the two most common elements in this class? Carbon and hydrogen. And you're probably rolling your eyes going, it's the only two elements we talk about, pretty much, with a leaving group here and there. And so structure, or the way that a molecule is connected together, is going to affect how the radiation interacts with each nucleus in the molecule. So to go back from my last slide, let's say you were comparing, this compound, which we call 1-butanol, versus this compound, which is 2-butanol. They're both C4H10O. There's no arguing that. But give me a thumbs up if you see that these molecules are connected in a different way. Right? They're connected in a different way. The atoms are not connected in the same way. I'll give you one proof. Look at this. This is a methyne. That's a CH. There is no CH in this entire molecule. And so what's going to happen is, since the protons, the hydrogen atoms, which we call protons, in the molecules are in slightly different environments, they're going to interact with that electromagnetic radiation in a different way. Anyhow, so protons and neutrons, let's go right down to the nucleus of an atom. Okay, we're going way down to the smallest part of an atom, which is the nucleus, right? You guys remember nuclei. We haven't talked about them a lot lately, but we are talking about nuclear magnetic resonance. So what's found in the nucleus? Protons and neutrons. You're like, Mr. Dion, I knew that already. Great, okay. Well, it turns out that protons and neutrons, which we often think about as like little spheres, they actually behave as if they're spinning, okay? They don't behave, or sorry, they don't spin like a spinning top, okay? But it is a useful analogy. So we can think of it as like a spinning top in a way, okay? And if you're like, what the heck does that have to do with anything? Well, you'll see in a second. Now, the next point is, it says if an atom has an odd number of protons and or neutrons, it's going to have nuclear spin. If it doesn't satisfy this requirement, so if it doesn't have an odd number of protons or an odd number of neutrons, it doesn't possess nuclear spin, and so we can't see it in the NMR spectrum. So what are some examples? Well, if you think about a hydrogen atom, okay, what's the most abundant isotope of hydrogen? It's hydrogen 1, okay, which just has one proton in the nucleus. Well, 1 is an odd number, and so hooray! That means that protons, which are very abundant, have nuclear spin, so we can see them in the NMR spectrum. Now, what about the most abundant isotope of carbon? It's actually carbon-12. That has 6 protons and 6 neutrons in the nucleus. Those are both even numbers, so you cannot see carbon-12, which again is the most abundant isotope of carbon. We don't see it in the NMR spectrum. But what about carbon-13? Carbon-13 has 7 neutrons, okay, in the nucleus, and therefore we can see carbon-13. Now, if you go back to your mass spec, you guys remember that little M+1? Well, carbon-13 is only about 1% abundant, okay? So that means out of 100 carbon atoms, 99 of them are carbon-12, and only one of them out of 100 is going to be carbon-13. You can't see carbon-12 at all. Okay, it doesn't have nuclear spin, so you can't see it in the spectrum. But again, out of every 100 carbon atoms, one of them is going to be a carbon-13, and we're talking about moles of atoms, right, Jenny? We're talking about huge numbers. So statistically, you're always going to have carbon-13 in your compound, and so you can see carbon-13 in an NMR spectrum. All right, does that make sense? You can't see the carbon-12, but again, every molecule is going to have carbon-13 in it. Why? Because it's 1% abundant. All right, so it says here that this spinning charge in the nucleus creates a magnetic moment. So what you have is, if you think about your nucleus that has net spin, okay, it has nuclear spin, it's going to spin around, and it has a charge, right? A nucleus has a charge. So if it spins around, it's going to create a magnetic moment, and a magnetic moment is the same thing as a magnetic field. Who remembers playing with magnets in grade school? Does anybody remember playing with magnets? I remember even in Canada, they had enough money to buy us a couple of bar magnets, Did anybody ever do this where you took a bar magnet in your fourth grade class or something with the North and the South Pole, and you put the iron filings around it, and it would make a little field lines that you could see? No, nobody's done this except me. Okay. Well, anyhow, let's move on from there. So here is a picture. A picture is worth 1,000 words, right? This is our nucleus. Okay. What we can think of as a nucleus, or we can imagine a nucleus as being like this. So this is your nucleus. Okay. You can imagine this being as a sphere, and it spins around like a top. Okay. And when it does, it creates a magnetic moment. Okay. And if we go back here, it said a magnetic moment is a magnetic moment is a magnetic field. So again, a magnetic moment is a magnetic field. Magnetic field, like that. So again, what's happening is you see this is the direction of the rotation, right? It's spinning around and around on this axis. Okay, so it's spinning around and around like a top. And when it does that, since the nucleus has a charge, right, it has a positive charge, it creates a magnetic field. And you see the field lines are coming out of the top and they're going down towards the bottom like this. Okay, you see a field line like this. And again, it's just like the field lines you would have seen with a bar magnet. Okay, it's a very similar thing. So if we have a magnetic moment in our nucleus, right, and we only have that when we have nuclear spin, so we have to have an odd number of protons or neutrons, it creates this magnetic moment, which is just a little magnetic field. Give me a thumbs up if you're with me so far. Like, okay, odd number of protons or neutrons. It has spin, nuclear spin. It spins around, and when I spin that charge, it makes a little magnetic field that we call a magnetic moment. Okay, now this is just a tiny magnetic field. Okay, it's very, very small, but it has big implications in just a second. So now what happens is, if you look at a bottle, okay, let's imagine you have a bottle of some kind of organic compound. Okay, so this is your organic compound and it's in a liquid phase. So we'll just say organic. Okay, some kind of organic compound. Well, you know that the molecules are just tumbling around inside that bottle. And so normally all the magnetic fields, all the magnetic moments, so it says here no magnet, all the magnetic moments, so these are just the directions of the magnetic moments, right? Again, the magnetic moment, you see that it's got a direction to it, right? So it's like this. Okay, so normally they're all just disordered. They're pointing in any way whatsoever. Okay, they're just completely randomized. But what's interesting is that when you apply a magnetic field, okay, B0, and remember, this comes from the spectrometer. This is that giant, strong magnet that I told you about. It was very powerful. When you subject your organic compound to a strong magnetic field, all of a sudden, the magnetic moments align with the magnetic field. So here, you see these blue lines here? These represent the externally applied magnetic field. When I say externally applied, that means the magnet in the spectrometer, okay? So when you apply that magnetic field, what happens is that all of the magnetic moments of the nuclei, they align with the magnetic field. So they kind of stand at attention, if you will, okay? And you see that some of them, what we call an alpha spin state, some of them align with the magnetic field, and then some of them are contrary, right? And they align against the magnetic field. But either way, they're all aligned in the same direction or the same orientation as the magnetic field. So what's so great about that? Well, it turns out that the alpha spin state, which is aligned with the magnetic field, is lower in energy than the beta spin state, which is the higher energy. Well, I guess it stands to reason. It's the higher energy spin state. Okay. So again, if you're wondering, where do these lines come from again? These are the magnetic moments, right? From the nucleus, right? Which is spinning around. You apply an external magnetic field. They kind of stand to attention. Some of them align with the magnetic field. Some of them align against it. But what's the consequence is that the beta spin state is higher in energy and the alpha spin state is lower in energy. And there's a very specific energy gap between the alpha spin state and the beta spin state. Is everybody with me so far? Give me a thumbs up if you're with me so far. Alpha spin state is aligned with the magnetic field. beta spin state is aligned against the magnetic field. Okay, you have to see a little bit more information before it'll start to crystallize in your brain. But anyhow, okay, so now where does the word resonance come from? It says when an atom in an alpha spin state, okay, if you take this atom that's in an alpha spin state, remember this is lower energy, is exposed to radio waves of just the right energy. Remember, the energy was directly proportional to frequency, right? Frequency is inversely proportional to wavelength, but either way, it's neither here nor there. When it's exposed with radio waves that are just the right energy, it's going to absorb a photon of energy and it's going to flip. Okay, we say it flips. It goes from the alpha spin state and it flips to the beta spin state. All right, and what turns out is that the stronger your magnetic field, the bigger the energy gap between the alpha and the beta spin state. Now we're going to actually look at this concept. We're going to look, I'm going to write down here later, okay? Because if you're wondering, well, why would I want to use a stronger magnet, have a bigger energy gap between the alpha and the beta spin state? I'll explain that later on. But right now, we can spin flip, right? We can subject a proton or a nucleus in the alpha spin state to a specific amount of energy, right, which is a photon of energy, right? Remember, light has a wave component and it also has a particle component, okay? So you subject it to a photon of light and it's going to spin flip to the beta spin state. It goes up to a higher energy state. Now, what happens is that the externally applied magnetic field, okay, which is B0, this is, again, this is the external magnetic field, okay, which is just a big magnet inside the spectrometer. The externally applied magnetic field also has another effect. Okay, so what do we know? What is going to surround our nucleus? Okay, in any nucleus you have, what's around the nucleus? Well, if the nucleus, right, the nucleus isn't going to be naked, right? So there's something surrounding it because the nucleus is positively charged. What surrounds a nucleus? Electrons, okay? So don't lose sight of things you learned in general chemistry, right? Around every nucleus, there's going to be electrons. So it turns out that that externally applied magnetic field has another effect. It causes the electrons that are around the nucleus, it causes them to circulate too. So now we have two things that are circulating. Not only is the nucleus circulating, which created the magnetic moment, which causes it to align with the magnetic field, but now the externally applied magnetic field causes the electrons. So that's what this ring is here. These are the electrons, okay, that start circulating around, okay? And what happens when we have a charge that's circulating? It creates a magnetic field. But you notice that the magnetic field that is caused from, or that is a consequence of the electron spinning, opposes the externally applied magnetic field. Okay, check it out. Look, the externally applied magnetic field is going in the up direction. You see that the magnetic field caused by the circulation of the electrons is going in the opposite direction. Okay, so what does that mean? It means that the nucleus, which can do the spin flip, okay, going from the alpha and the beta spin state, is going to feel a little less of that magnetic field if it has more electrons around it. If you're not following me, look, listen very carefully. Okay, the more electrons I have surrounding my nucleus, the greater the magnetic field is going to be that's opposing the externally applied magnetic field. If I only have like a little bit of electron density around here, you're only going to have a little field opposing that externally applied magnetic field. So based off of the amount of electron density around your nucleus, that's going to cause the absorption of light to be at different frequencies, right? Because it's going to take different energies to do the spin flip. So therefore, it says, causes electrons to circulate, inducing an opposing magnetic field. What I was just describing, we call that diamagnetism. Everything on this planet has diamagnetism, even me, because we all possess electrons. And it says that nuclei then experience less of the externally applied magnetic field, which again is B0. And when they experience less of that externally applied magnetic field, we say that they are shielded, okay? It kind of blocks them, right? So this is shielding, right? It's blocking some of this, a little bit of it, okay? Now, what's the consequence of all that? Again, if they're shielded, it requires less energy to spin flip. And we know that energy was what? Directly proportional to frequency. So that means that protons that are in, or nuclei, I should say, that are in different electronic environments are going to absorb different frequencies of electromagnetic radiation, and we can plot that. Okay, that's the whole, that's what an NMR spectrum is. So nuclei surrounded by less electron density are de-shielded. So again, if you have a lot of electron density around your nucleus, it's shielded. If you have less electron density around your nucleus, it is de-shielded. All right. So now that we've unpacked that, it says the amount of radio wave energy. So the amount of energy that you need to go from the alpha spin state to the beta spin state, like I just said, depends on the electronic environment of the atom. Why would that be? Let's unpack it again. Because energy is directly proportional to frequency, but it's also directly proportional to B0. And the amount of B0, the externally applied magnetic field that the nucleus is going to experience, has to do with whether it's shielded, or de-shielded. So again, and I'm repeating the same thing over and over here, my friends. I've probably said this 3 times already. So again, what's the consequence? If the nucleus is in a different electron environment, okay, it's going to absorb a different frequency of electromagnetic radiation, and we can plot that. So when the alpha spin states are flipped to beta spin states, energy gets absorbed. That's where the word resonance comes from. So when the energy is absorbed, maybe I'll unhighlight that. When it flips from the alpha spin state to the beta spin state, that's what resonance is. It has nothing to do with the resonance in chapter 2. Hear ye, hear ye. We're talking about 2 completely different things. Resonance in chapter 2 doesn't apply to this chapter whatsoever. And if you're like the same word twice in the same subject, but it means 2 different things, what are the odds? I don't know. Probably not good, but that's what it is, okay? So the total amount of energy required for each proton to spin flip tells us about its electronic environment, and it tells us about the structure of the compound. Now, before we get into some more detail on shielding and de-shielding, let's talk a little bit about how you acquire an NMR spectrum. Now, I'll just back up to the picture of the spectrometer here, because maybe you guys don't have an idea of the scale of the spectrometer. But I don't know, a human being would be something like, I don't know, it depends on the person, I guess, but maybe Mr. Dion would be something like this, you know? So you take your sample, and then you put your sample in the spectrometer here. And your sample is not very big. It's more like your sample is like this, okay? It's a very small tube, and you put it in the spectrometer, and then it goes down into the inside of the spectrometer, and it gets spun around. So it gets spun around, and that just, you know, minimizes imperfections in the tube or whatever. But this is your sample, okay? So this is your NMR sample, is in this little tiny tube, and then you put it inside the magnet, okay? So this is your, well, I already had it labeled magnet. So you put it inside the spectrometer or the magnet, and then, yeah, then you run your NMR spectrum. So to go back to section 15.2, where is it? Right here, it says, NMR requires a very strong magnetic field. Okay, so we already talked about that. And it says the strength of the magnetic field establishes the energy gap between the spin states. We talked about that too. Now, you guys remember probably from physics class or maybe a physical science class that magnetic field strengths are measured in Tesla. So magnetic fields are measured in Tesla. And that's not really a huge thing. It's just the idea that the higher the magnetic field is, the bigger the energy gap. And remember, I said, and this is probably the 5th time I've said this today, that energy is directly proportional to frequency, which is directly proportional to magnetic field strength. So if frequency and magnetic field strength are directly proportional, what the consequence of that is, we don't ever describe our magnet in terms of its magnetic field strength. We don't describe our spectrometers that way. It turns out that if you have a magnet that has a field strength of about 1.41 Tesla, all of the nuclei that go into that spectrometer are going to resonate at a frequency of about 60 megahertz, okay? Whereas if you have a field strength that's 7.04 Tesla, all nuclei are going to resonate at a frequency of about 300 megahertz. So we would say I have a 60 megahertz, you know, spectrometer. At this university, they have a 300 megahertz, and you can even have, like I've seen an 800 megahertz. I never touched it, but I've seen one, okay? But anyhow, now just to put it in the simplest possible terms, why would you want to have a stronger magnetic field and a higher operating frequency? So what's the difference between a 300 and a 60 megahertz spectrometer? I can tell you in kind of layman's terms. You want me to explain it to you? It's this. Has anybody here ever seen like an old tube TV? You guys might be too young, but I grew up watching a tube TV. So meaning like the screen is glass, okay? Okay, can you watch it or an old black and white TV? Can you watch a movie on it? Sure. You get the story? Yep, absolutely. However, what looks better? Can you watch the same movie on in HD, on a brand new, 50-inch flat screen TV? Yes. Okay, you get the same story both ways, but you get a lot more detail with the more expensive TV, don't you? Okay, and that's kind of the way it is with the more expensive spectrometer. You get the same information, you can run the same spectrum, but you get more detail, and that detail can be really important sometimes when you have protons that resonate close together. Anyhow, you'll see that more later on. Now, what about this super strong magnetic field, this 1.41 Tesla magnet, or whatever it was, a 7.04 Tesla magnet? How do you get a magnet like that? Okay, you can't just buy one at the store. Well, has anybody here ever made an electromagnet before? Has anybody ever made an Isaac, you ever made an electromagnet? Or Jenny, has anybody ever done that? So you take a nail and then you wrap wire around it like this, and then you hook it up to a battery. So let's say you have a 9-volt battery or something. You have the two terminals and you hook one up to the cathode, one up. Has anybody made an electromagnet before? Yeah, okay. So Lauren did in physics class. So electromagnet. If you've never made one, you should try making one. Just take a nail, like a big spike or something, and wrap a wire around it and hook it up to a battery, my friend. You'll have yourself a magnet, okay? And that's a pretty cheap way of doing it. You can make it for what, like $5, okay? But this very strong magnetic field in an NMR spectrometer or an MRI, okay, it's made the same way, is they take a really strong current. So they take a lot of electricity and they pass it through a superconducting material. And then if I don't know if, and I'm not going to go into the details of this, but if you lower the temperature, it conducts even better. And so you get a stronger magnetic field. So they lower the temperature down to 4 Kelvin, which is pretty close to absolute zero. So what that means is inside that big old spectrometer, so I don't know what the spectrometer looked like a couple of slides ago, but it looked like something like this, okay? So inside the spectrometer, the temperature is about 4 Kelvin. If you're wondering, well, how the heck do they make it that cold? That's a good question. The way they do it is with liquid helium. So helium in the liquid phase. So helium, is a gas at room temperature. But if you cool it enough, it's a liquid. And liquid helium has a temperature, I think it's like 4.2 Kelvin or something like that. So it's pretty close. Now, if you're wondering, well, how do they keep it that cold? It's inside a jacket of liquid nitrogen, which is at 77 Kelvin, and then they have another jacket outside. So if you go back to the spectrometer at the beginning, inside, you've got the liquid helium. I can use a finer tip pen. There we go. Inside, you have liquid helium, and then that's inside a jacket, which is liquid nitrogen. And then you have another like vacuum outside of that, a vacuum flask outside of that, like I don't know, like a Yeti or something, like a Yeti mug or something. Okay, so that means that inside the spectrometer, it's around 4 Kelvin. So yes, it's very cold inside the spectrometer. Anyhow, really cold. I don't want to be inside a spectrometer. Too cold for me. All right, so there you go. Now, what we do is when we put the sample inside the magnet, is you pulse it with all the relevant frequencies of electromagnetic radiation that are going to cause resonance to occur. And we call that a pulsed Fourier transform spectrometer. So it turns out it's not a huge range of wavelengths, but they're all in the neighborhood of, let's say you have that 300 megahertz spectrometer. It's going to be something like 300 million to 300 million 5,000 megahertz. Okay, so they're all very, very close to each other. And then you excite the sample. What does it mean to excite the sample? It means the alpha goes to beta. And then when it relaxes, so relaxing is when it goes from beta back down to alpha, it emits energy and we can record that energy, right? The energy goes into something called a receiver coil and we get what's called a free induction decay, okay? And we do what's called the Fourier transform, which is just a complex mathematical equation. And then after the Fourier transform, you end up with your spectrum. Okay, so it says the FID, or the free induction decay, contains all the information for every single atom. Then you do this complex mathematical treatment that we call a Fourier transform, and it separates the signals so you can see each signal very clearly in the spectrum. And normally we take a bunch of FIDs, so we pulse the sample, or we hit it with all relevant frequencies of electromagnetic radiation over and over and over. Sometimes we'll do it 100 times. Okay, it's usually some multiple of 8. So 8, 16, 32, 64, 128, 256, 512, 1028, et cetera, et cetera. And then you average them all together to get the best NMR spectrum you can. Now, it says here, before analysis, an NMR sample has to be prepared neat. So if it's neat, neat just means no solvent, or in a liquid solution, which is in a deuterated solvent. Now, if you think about it, in a solution, you have what? You have the solute and you have the solvent. Okay, well, the solute, if you dissolve your compound, the solute is going to be the compound that you're interested in, and the solvent is going to be the solvent. Okay, now which one's present in a greater amount? Is it the solute or the solvent? Could anybody answer that? What's present in them? If you put Kool-Aid in water, what's present in a larger amount? The solute or the solvent? Could anybody answer that? And it's not a trick question, me trying to get you or something. It's the solvent, right? By a long shot, okay? It's going to be like almost 100% solvent, or maybe 99% solvent. So if your solvent has protons in it, what do you see in your NMR? Just solvent. So that's useless, totally useless, good for nothing, okay? So if you're like, well, how do I work around that? Good question. The way you do that is you use what's called a deuterated solvent. So we replace all the hydrogens in our solvent, we replace them with deuterium. So instead of having H2O, forget that, it doesn't work. You use D2O, because deuterium is not going to show up in your NMR spectrum. Now, if you're very astute, and I know you all are, you know that deuterium is hydrogen 2, right? That's what deuterium is. Now, you could say, well, that's got an odd number of protons and an odd number of neutrons. Doesn't that have nuclear spin? Ah, very good. It does. It does have nuclear spin. You're right. It turns out, though, the deuterium doesn't resonate at the same frequencies. So that's why you don't see it in the NMR spectrum. Okay, so you just forget about it. It doesn't even show up on your spectrum at all. So there you go. You spin the tube around, and that's done by the spectrometer for you, and it spins it quickly, and that's just to kind of average the sample out. It's just to make sure it's mixed properly, and it limits any imperfections in the tube. This is what an FID looks like. You don't really have to know much about the FID, because to go from the FID to a spectrum takes literally one mouse click. Okay, so the computer does the work for you. Okay, don't worry, you don't have to run any Fourier transforms. Fourier transform is just complex math is all it is, and it does all the work for you. Anyhow, all right, sorry you guys, I'm going on, but we'll do one more slide and then we'll take a break. So what are some common deuterated solvents, right? I told you that one of them would be D2O instead of H2O. Another one, instead of chloroform, which is CHCl3, you get rid of the hydrogen and you replace it with deuterium, and you get CdCl3, which is shown here. Another one that I used to use a lot is, you guys remember in chapter 7, I mentioned this compound. It's called dimethyl sulfoxide. Well, it's got 6 hydrogen atoms in it. So what you do is you replace all of those with deuterium, and you get CD. There you go. So you replace all, and we call this DMSO D6. Don't ask me why we use a lowercase d, but anyhow. So there you go, DMSO D6. But the bottom line is you just get rid of all the hydrogens in your solvent. There you go. So this is, again, ooh, this is a scary looking spectrometer. It's all spray painted dark here and brooding or something. But anyhow, the bottom line is this is your spectrometer. You've got a superconducting magnet inside. Your sample is in a very tiny tube that goes in here. The inside is at 4 Kelvin. You have a jacket outside that's at 77 Kelvin. This one is liquid nitrogen. This one is liquid helium. And then outside you have a vacuum flask like that. This is your radio frequency generator here. You can see somebody's got an FID on their computer screen here. They haven't processed it yet. But anyhow, there you go. That's what an NMR spectrometer looks like. I hope that gives you a little bit of an idea of, what an NMR spectrum, how it's processed and, why it works. Okay. Now, if you're saying, I haven't even seen an NMR spectrum yet, what does it look like? Well, we're going to get to that. Okay. This is an NMR spectrum right here. This is a proton NMR. And we're going to get into this after the break. And we're going to talk about all the different types of structural information that you can get from an NMR spectrum. So we're going to talk about the number of signals, where they're located, which we call the chemical shift, the intensity, and the shape. And then we'll be able to get more information about what do we actually get from the NMR spectrum. All right.